recording this on my computer because who knows how the cloud recording is going to be with my poor internet. And if it cuts out, my on-computer recording will be flawless. And I'll get that onto YouTube here as soon as class is over. And it's going to look a little bit different because your pictures will show up on the YouTube recording. Okay, so we're looking at chapter 20, which is dealing with organic chem. Now, organic chem is far more than just a chapter in reality. Next year, some of you will be taking it as your next chemistry class, and organics is one of the classes that's going to probably give you nightmares and ruin your social life. And here we're just going to get a taste of it. Now, I hit the wrong button. I hit end rather than page down. Where the name comes from. Organic was at one point study of organic molecules as in coming out of organic living creatures. It's now much more classically defined as something that contains carbon in it. Now, for the most part, hydrocarbons, molecules with just carbons and hydrogens, make up a very, very small portion of organic molecules. Now, those are going to be the category that we learn how to name really, really well. All the other organic molecules involve adding some other nonmetals to them, like nitrogen, oxygen, fluorine, phosphorus, sulfur, chlorine, bromine, iodine. And we will see how we go about naming some of those. But we're really not going to do anything in this chapter about how to make any of those compounds. So no chemical reactions. Which is disappointing. I mean, matter of fact, if we were doing this class for real and you were in the lab, this is a term you would have got the chance to make aspirin from salicylic acid. But you didn't get to do that. Maybe in theory, but not for real. Okay. Why is carbon so darn important? Has a lot to do with where it's at in the periodic table. It's right in the middle of electronegativity, so it typically likes to make a covalent bond with just about everything. It does like to make 4 bonds, either 4 single bonds or a combination of double or pi bonds and single bonds. And once it makes these bonds, they're relatively stable, so you got a lot of stability in the molecule itself. But those contributing factors lead to a huge amount of variety. For instance, now before I get to my for instance, I'm going to introduce how we're going to draw these some, because obviously having nothing but carbons and hydrogens, these molecules can get quite kind of big. I mean, the first 2, methane or ethane, are ones that we've talked about before. Next one is pentane. Pent coming from the fact it has 5 carbons. These go up tremendously. Octane, for instance, like what you see an octane rating on a car. Octane, the oct means 8. So octane in its raw form is C8H18. And I'm going to do this condensed structure. So it would be CH3, CH2, 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 1, 2, 3, CH2, CH3. That would be octane. Now, ironically, that particular molecule is not found in gasoline at all, or very, very slim. And yet, the octane rating seems to imply it's there. Whereas actually making the octane rating is something that's probably more called isooctane. So it's an isomer of octane, and those 8 carbons are arranged slightly differently than just a straight line. But these Lewis structures and the condensed structures down below are actually shown to give us a little bit more of an idea of how they're laid out. And we're going to see some more of those. And the biggest reason we do that is because the complexity that pops up on organic molecules very, very quickly. Like on the far left here, I have the exact same formula of the molecule on the far right. The only thing that's done differently is on the far right, we've left out all the hydrogens. And we've shown the carbons with roughly close to the bond angles we'd expect them to have if we're looking down on a piece of paper. So each of these are 109.5 degree angles, but technically they're coming up and out of the paper. So that's why it all looks like 120s. And as a matter of fact, the program I use to actually make molecules like this, I can't see it because it's behind you guys. Are you seeing something now that says Marvin Sketch? Okay. Well, if I were to draw this molecule over here and try to draw it nice and straight like they had it in that picture that's right between my screen, I can do that. But see how hard it makes it to see things? Because everything overlaps with itself. Where this gets neat, Marvin knows that that's a bad way to do it, and if I tell it to clean up the structure, look what it turns it into. It's essentially this, just ever so slightly rotated to look a little bit more confusing. But it gets those, looks like 120 degree bond angles. And it does what they call a skeletal structure by default. So the carbons are not explicitly drawn, yet these other two guys coming off here are actually hydrogens. And I can label them. But when I actually optimize this structure, it may or may not leave them there. Yeah, it's going to leave them in this case. Because it thinks I'm drawing attention to that location a lot more. But if I go back and erase them, and clean up that structure again, I'll go right back to kind of what it was. Alright, now the reason this is darn important really has to do with the complexity of organic molecules and how quickly they get complex. We will see expanded forms in a lot of cases where the hydrogens are explicitly drawn and you're seeing the hydrogen bonds, like the CH bonds in there. But more often than not, we get condensed structures or skeletal structures just for that speed of drawing them. And even on things, like I mentioned that if we were doing a real lab, you might get to do aspirin. If I go to Wikipedia and type in aspirin, look at the structure it gives. It's right there. It's just my dark mode. It is one of these skeletal drawings. So you're not seeing any specific carbons drawn, and only one hydrogen is drawn. And it is specific because it's off to that oxygen. But anything else that ends with a line, that's supposed to be a carbon. And that one, for instance, since it's only got one bond, and carbon likes to make 4, the other 3 things must be hydrogens. But they just leave that off because it's simpler. And this is to explain how we could figure out how many hydrogens are actually missing. So if you see a carbon on the end and it has nothing else, you assume it's missing 3 things. Those must be hydrogens. In the middle, that carbon there only shows 2 things bound to. The other 2 things must be hydrogens. Only one thing, or one thing missing, so it must be a hydrogen. And if you see a carbon with 4 bonds, it's not missing anything. That does count as 2 bonds on that one there, so this is missing 2 hydrogens, yet this one is only missing 1 because it's got 3 bonds. So we can always figure out how many hydrogens are missing by how it's drawn. Alright, so let's see if we can figure out how many hydrogens are on each of these molecules. So like on the left here, I have a formula with carbons, 1, 2, 3, 4, 5, 6, 7 carbons. How many hydrogens up here off this upper right one?
3.
Mm-hmm. Right next to it.
So there must be 1 on that.
Mm-hmm.
And 2 on each of the other corners.
2, 4, 6, 8, 10, 11, 12, 13, 14. Five carbons. How many on this end?
2 on each of the internal corners, and then 3 on the end.
Now, I know when it comes to fats, you've heard of the phrase saturated and unsaturated.
Yeah.
That's related to hydrocarbons themselves. A saturated hydrocarbon has as many hydrogens as possible, and that fits this category right here. There are no double bonds, so it is saturated. And if you have a saturated hydrocarbon, the number of hydrogens is always twice the number of carbons plus 2. The reason this is less, it's still saturated because it's nothing but single bonds, but the reason it has 2 less hydrogens is because it's a ring. Because kind of what you're doing, be like taking the end here and connecting it. You'd have to remove hydrogens to do that. One from each of those ends. Alright, how about here? Can we make that call on the number of hydrogens just from the number of carbons then? 2, 3, 4, 5, 6, 7 carbons. So how many hydrogens would you predict on that first one? Two times 7 is 14, plus 2 is 16. Let's see if that works. 1, 2, 3. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This one over here is the exact same thing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now, interesting, naming these, 7, the prefix that's kind of Greekish or Latin, would be hept. This guy over here is actually called heptane. Hept for 7, ane for hydrocarbon with single bonds. The A is not heptane though. And it's because heptane implies 7 in a row. And this does not have 7 carbons in a row. We'll see how to name that here shortly. And the reason it's darn important to see how to name them is obviously you can see how complex this gets as soon as I start doing heteroatoms. Everything on this page is made with 4 carbons and 1 oxygen. And I'm almost positive I have all of them on here. And the only one of these that is probably something you've even heard of is this top, the very top one up here. Used to knock people out with something they called ether. This is, when you hear the word ether, that's what they're talking about. Now, more specifically, this one is diethyl ether. Because that 2 carbons is an ethyl group, and there's 2 of them. Now, interesting thing about diethyl ether, calling it ether, that's not necessarily wrong. Even though there are other ethers, this thing down here is also ether. We don't ever call that one ether. When you use the name just plain ether, it's implied to be diethyl ether because of the medical use that used to be much more common. We don't use it at all for that anymore. Let's see, is there another one on here? There should be. I just got to find it. This guy right here, if you've ever been to the paint store, you might have seen a solvent called MEK. that name comes from methyl, this guy over here on the end, and ethyl, this guy over here, and this guy in the middle is called a ketone. So this is methyl ethyl ketone, and it's used as a paint thinner. It actually smells kind of nice. And I don't think any of these others are common enough. I'm going to highlight a couple. Like this guy right here with that 3-membered ring and the oxygen. That 3-membered ring with an oxygen is something we call an epoxide. So if you've ever heard of epoxides, a type of glue, they all have that common feature in them. Now, there isn't a epoxide, which is kind of weird because if you go to a store to buy epoxide, it seems like there's only one. There's a common one, but it's not super common. Ironically, they all do the same thing, so we can call it epoxide, and that's good enough for the masses. All right, but we're going to see how to name many of these, but not all of them. Now, what we are going to learn is how to identify certain functional groups. I'm going to change my highlighter color. So like this guy right here and this one right here, and I saw another one right below it. And there should be one more that's got the 4 carbons. There it is. Those are all just alcohols. And matter of fact, even coming off a ring like there, or off this, or there, having the OH right together, that makes up an alcohol. Now, interesting, you've probably heard of alcohols as something you can consume. None of these would be a good idea to drink, because your body can't process any of those alcohols. I'm not even sure if your body would do anything at all. They might actually just pass through. Could be toxic. Let's not chance it, right?
Yeah.
Yeah. But we'll actually learn a little bit more about those. But the ones that we will be naming are the ones that have just carbons and hydrogens. Like everything on this page, we will eventually learn how to name. Now, right now, the only one I feel confident saying that we could name is this very top one. Because, yeah, it's got the 5 carbons in a row. 5 in a row. Oops. I'm still on highlighter. It's just pentane.
Let's see. Oh, alright.
Now, these two in the middle, at the bottom, those are actually also just pent, but they'll have an E-N-E for a suffix name. And we'll have to say where the double bond is. So we're going to add to the naming, but these are actually just E-N-E. So I'm going to put that here in the end. So E-N-Es, and these are going to all end in A-N-Es. That comes from alkanes and alkenes. Aren't those cool names? Now, interesting thing with the rings, since the rings also have just nothing but carbon and hydrogens with single bonds, they're also going to have the A-N-E suffix, but we're going to have the cyclo prefix. Now, don't worry about it. We're going to be coming back to this page because we're going to actually name every single thing on this page once we've introduced all of our naming rules. Okay. For instance, what we could do for practice, and this is a great example. All right, I should be back on Zoom just a second, so hang on. Sorry, folks.
Oh dear.
Am I back up and visible for you too?
You there?
I am here. Are you able to hear me? I'm stopping your video.
Disappeared for a minute.
Yeah, I know. It froze up on me here. I lost internet. Morgan and Kelly, I'm stopping your videos. And hopefully that still works fine. And hopefully that'll ease up on that congestion that we were experiencing. Can you guys still hear me? Kelly, are you able to hear me?
Let's test if it's still working. Morgan, can you hear me?
Yeah.
Oh, okay. This is peculiar.
Can either of you hear me? All right, can you hear me now?
Yeah.
Okay. When it reconnected, it had muted me, and I'm not paying attention to that. I muted your videos. That should help that stability. At least I hope. But
yeah,
we'll find out. I'm recording it live, so even if I don't reconnect, it'll be on here, and it's working fine. Okay. So this question here wanted us to actually identify all the compounds that had 6 carbons with no multiple bonds and no rings. So to do this, I'm going to draw at first. It's not even really a skeletal or condensed structure, because I'm actually just going to draw carbons. And the easiest way would be to put them 4 in a row, or 6 in a row, since there's 6 carbons. Then I'm going to back up and add the hydrogens that would be missing. So this first one needs 3 hydrogens, since there's only one thing to it. We would need 2 there, 2 there, 2 there, 2 there, and 3 there. And in theory, we could name this one already. What do you think this one might be called?
Hexane?
That's right. Okay, now an easy derivative of that, I'm going to still do the 6 carbons, but let's rip that very end one off and put it somewhere else other than one of the ends. So what I mean by that, I'm going to rip one of those H's off there and attach that CH3 off that location. And then put everything else roughly the same, except on this one, where I'd ripped off the H here, I'm going to put it back at this location. And do you see how I could have done that and moved that CH3 here to the middle and got something totally different? Now, because geometry the way it is, if I were to somehow try to put that methyl down here on this end, wouldn't you see that that's just the same as this thing backwards? So this really is the only way we can take that in location and put it off these 5 carbons. Because if I put it off the very beginning, I'm just drawing hexane again. So I can only put it off that second location or that third location. Now there still are others. We're going to do that again with another carbon. Move it here and there.
Why couldn't you put it off the 4th location?
So like this?
Yeah, basically. Oh, because that's just the same as before, but backwards.
Yeah.
Oh, okay, never mind. Sorry.
What are you guys seeing on your computer screen right now?
I'm watching your screen recorder
Yeah.
program.
I thought so. My little program that I write on just crashed, which hasn't really actually ever happened. There we go. Yeah. These two are the same thing. Here's the only thing. We could say it's 5 carbons in a row, and we're branched off the second location, or it's 5 carbons in a row and we're branched off the second location. Just have to count from the opposite direction. Alright. We do have some others. We're going to do 4 in a row. Now if I attach either one of the methyls off the beginning or the end, that would change it back to 5 in a row. So I need to put the other 2 off these 2 locations. And there's exactly one more way to draw this where it doesn't have a ring, and that's where we're going to take those 2 methyls and add them to just one of these carbons when there's 4 in a row.
So, what do you call it? So we've got basically hexane, but with one of the carbons off to the side. What do we call that?
Well, so the term we use when they come off of the side of a molecule, and it doesn't matter if it's a methyl or just anything else, we call these things substituents. So what we kind of have on this last molecule I drew, we have the backbone, which is going to give the name of the molecule. And it turns out 4 carbons, and I'm gonna skip a page and then come back to this. We've been talking about these prefixes telling us how many carbons they are. Well, they make sense after 5. Pentane, hexane, heptane, octane, nonane, decane, from the prefixes. It's the previous 4 that don't necessarily actually translate to anything we've necessarily seen, because these were all derived by where we first found them. Now, prop kind of means first or simplest, and that's because propane was found or first derived from the simplest fats and sugars found in mammals. And bute for butane was found in butter. But that's where these first 4 come from, names like that. But on this thing, this backbone is actually butane. And the methyls, the CH3s, they are just methyls because they're only 1 carbon. Meth. And then the YL tells you it's a substituent. And substituent just means it comes off the backbone.
I see. So if you had a 4 carbon substituent, it would be butyl?
Yes, it will.
Okay, alright.
Now, technically there's not a space here. This is actually dimethylbutane, all one word. But you see up here right above it, this would also be a butane and dimethyl. So they can't both be dimethyl.
So how do we distinguish?
Right. So we're going to distinguish them based on where the branches actually are. So we're always going to number a backbone. Like on this bottom one, we number it 1, 2, 3, and 4. So where are both those methyl groups?
On number 2.
2, 2, dimethyl. Up here we number it 1, 2, 3, 4. So this one is 2, 3. Yeah.
So let's see. Um, the second and third ones on the, I guess they'd be second and third. They would be, that is 5. So that would be pentane. So 2-methyl pentane.
That is correct.
And 3-methyl pentane.
That is correct.
All right, cool.
Now, on that 2-methyl pentane, do you see if you had numbered it the backwards way, you would have got 4-methyl pentane? So if I'd numbered up here 1, 2, 3, it would have been 4.
Mm-hmm.
Well, when you decide your backbone, you don't necessarily decide which way is the front way and which way is back way. We decide that based on the substituents. We want the substituents to be closest to the beginning of your chain. So like on that 2-methyl pentane, since it could have been 2 or 4, 2 is a lower number, it's going to be 2.
All right.
All right, now what we just summarized really was these rules. We're always going to find this longest continuous chain of carbons, and then we're going to identify the substituents. And I did that with a box, and then I circled them. Now, we don't number the backbone until we've identified the substituents, because we want this to be lowest numbers. I'm just going to say numbers. Now, alphabetize the substituents is going to apply when we have more than one substituent off that are different. So if I had, I'll do this with a chlorine and a bromine. See, that's still a butane?
Mm-hmm.
And how would you number the backbone, you think? Which way? Which carbon's number 1? On the right here or the left?
Well, if we're going to alphabetize it... Oh. Wait. If we're going to alphabetize it, then I guess the bromine is closer to the front.
That is correct. Yep. So this thing is 2-bromo. Bromo is telling us a substituent it's a bromine substituent. And then 3-chloro. Butane. And these last two really are how we put it together. You're always going to alphabetize your substituents. And you're going to separate the substituents with numbers. And you know on that previous page we had this di pop up? That was because there were 2 methyls. When we alphabetize, though, we alphabetize by the M for the methyl, because it's the methyl that's being alphabetized, not the di. All right, let's actually practice some of this, but we're going to introduce something kind of crazy first. All right, now, Kelly, you had actually pointed out that if it was 4, it was butyl. And I said yes, and that is true. If it's 4 in a row and you're branched on the end, it is definitely the butyl group. But here's the interesting thing. 4 carbons could be arranged differently. You could have 4 in a row and you're actually attached to that second one. Or your 4 might not be in a row. Well, that creates these different names. Now, I'm going to underline where we alphabetize this. This first one we do alphabetize by the butyl. This one we also alphabetize by butyl. And this one we alphabetize by butyl. Because that sec and tert, secondary is more of a geometry term. Secondary, tertiary. What those numbers are applying to is the carbon you're branched to is secondary because it's connected to 2 other carbons. And this carbon is attached to 3 different carbons, so it's tertiary. And because of that, you don't alphabetize by the S and the T. Now here's interesting. Isobutyl, you do alphabetize by the I. Isn't that weird? So that means this isopropyl you alphabetize by the I, but propyl you just alphabetize by the P. Now, theoretically, they go higher than this, and there are pentyls. It's safe to consider that too complex for organic chem right now. Because this table changes there, and we get these own unique little rules for complex substituents. Alright, so let's try to practice one of these, following all these rules. So the very first thing we always do is find the longest continuous chain. Now, it may or may not go flat across, but what we would do is you would find an intersection, like this one here that has 4, and we want to go the direction that gets us the longest possible way. And all 3 of these are just CH3s, so it doesn't make a difference which one we go to. So I'm just going to make it nice and pretty and go straight across. And this is a CH2. I'm going to include that, and then I get here, and you see how it won't matter which direction I go because they both go to CH3s. Because of that, I'm just going to go straight across. And that created 1, 2, 3 substituents. Alright, now I have 2 different ways I could number this. 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. Which way do you think is better?
Arbitrarily.
Because this doesn't seem like it makes a difference, does it? Because they're either at 2 and 4 or 2 and 4. But let me put this name all together and let's see if we can see why one might be better. So it is 3 methyls. So my full name is going to be a trimethyl. And then 5 in a row pentane. And we do want to label what all 3 are. So if I label it with my orange color, it would be 2, 2, 4. And if I number it with the green is 2, 4, 4. Now do you have an idea of which one might be better?
I do.
Yeah, because the 2 is kind of like a tiebreaker. There's 2 at that location. Now you will find in real organic or the full semester organic chem, the expansion to these rules right here are where it gets complex. Because there's plenty of reasons that you get ties and you have to have multiple ways to have tiebreakers. This was just one of those first ones we talk about. When there's more than one substituent, that location ends up taking priority. Alright, let's try some others. Now, you'll see that a couple of these are the exact same thing. But I did it this way so we could see how that backbone may change. So, like we have this weird intersection here. You see how this side would be a much better way to go than straight down? And I go to this carbon right here, but do you think I should go straight on over or should I go up? Yeah, I should go up. Because I get more carbons that way. And that turns these guys into just substituents. And then numbering, I have 1, 2, 3, 4, or 1, 2, 3, 4. See how it doesn't make a difference? They're either at 3 and 4 or 3 and 4. And there's no reason to have one tie over the other, so it doesn't matter which structure we number this one. But it gives us 3, 4, dimethyl, hexane. All right, going to the right, what do you think the backbone is? How many carbons are in the backbone?
4, so that would be butane, and a methyl at, what is it, at 2, I guess. I don't know what you would call that, at section 2, region 2, whatever.
Carbon 2.
Carbon 2, okay, there we go. So 2-methyl butane.
Very good. This one's too easy.
The next one's 3-methylhexane.
Yeah. It's real easy when they kept in a straight line like that, isn't it? Even this one.
Indeed. That's butane, so 2-methylbutane.
Well, that's weird. That's the same as the upper middle one. Doesn't look the same though, does it? Is one of those wrong?
Well, you could I wouldn't say anything is wrong because it just means that it's bent and not straight.
Correct. It's rotated in space. Yep. Which is what happened here too. Makes it look a little bit more complex.
Yeah. But it's still just 3-methylhexane.
It is. And what is this guy then?
2,3-dimethylhexane, pentane.
That is correct. All right, now, before we do these, because they're easy, I want to go back and do these. The 2 we can do. So this column over here. And we've kind of just did this one. What are we going to call that one?
Well, that would be 2-methylbutane.
Mm-hmm. And
well, that would be 2-dimethyl. What is it? Ethyl. Wait, why is it ethyl? Why wouldn't it be?
no, that's dimethyl.
Methyl.
It is methyl. Dimethyl.
Oh, okay. Oh, okay. I see. So dimethylpropane. I see.
All right, now the next thing we're actually going to kind of cover is these rings and that double bond. And I'm not going to bother to do this practice. Those are easy. The rings we are going to name basically the exact same way, but we're going to actually give the backbone name just to the ring itself. So you're going to use cyclo to say you have a ring, and then say how many carbons are in that ring. So that's how these get to be cyclopropane and cyclobutane. Now, what they're kind of showing on this three-dimensional perspective drawing, you see how it kind of looks like this square might be kind of puckered or bent? It's because it kind of is. The structure is twisting ever so slightly to get the hydrogens slightly further away from themselves as they were. It gives that molecule a little bit more strength by letting the hydrogens get just ever so slightly further away. But it also means we have a square that doesn't have right angles. These internal angles are closer to 89 degrees. Isn't that weird? Because it's no longer flat. Now, this cyclopropane is perfectly flat. And those hydrogens are that's why this thing looks super symmetric, because it actually is. Now, keep this in mind with cyclobutane. Since it doesn't have to remain planar, cyclopentane and cyclohexane actually are very similar in their structure to just regular old carbon. So even though bond angles of a pentagon and hexagon are nowhere near 109 degrees, the actual structures are very close to 109 degrees because they no longer stay flat, they kind of pucker. Matter of fact, this guy, you see that kind of a weird zigzag pattern it gives? If you take organic chemistry, you get used to drawing these, and they're so beneficial that something you can find on something like Amazon or organic stencils, like the old plastic trays that you put on paper to trace things, but you can get stencils to actually draw your conformers of cyclohexane. Isn't that weird? And you can actually buy graph paper for organic chemistry that's just a bunch of hexagons rather than squares. And it's because of these. Alright, now when we branch something off of them, I don't want to do that yet, we're just going to name it as a substituent. So we kind of can do the rings here, like this 5 in a row, that is just cyclopentane. That's all we do is add the name to it. So what do you think the backbone is of this one?
Okay, sorry, I was muted. That would be butane.
Yeah.
So it'd be cyclobutane plus a methyl. And I have no idea where you would put that.
The neat thing is, we actually, if it has just a single substituent, we just say methyl cyclobutane.
Okay.
When there are two, so down here at this very bottom one, because there's more room, there are two different substituents. You're going to say that one of them is at number 1. It'd be whichever one comes alphabetically first. But since these are both methyls, doesn't matter. So I'm just going to say one of them is number 1. Where is the other one at then? My ring is either 1, 2, 3 or 1, 2, 3. Notice how we like to do low numbers? That's what we do. 1, 2, dimethyl, cyclopropane. What do you think this one might be called?
Oh Lord, okay, so 1,1 dimethyl cyclobutane or cyclopropane.
That is right. I can make that look prettier. And you notice the difference here? Now I have this carbon connected up here, so this is just one substituent. So what is this other one called?
Well, let's see here. It's methyl. What is here? I don't remember what the prefix is.
Oh, for 2 carbons, it's just an E for ethyl.
Oh, ethyl, yeah. Okay. So, so it'd just be ethyl cyclopropane, okay.
Yeah, no number because there's only one substituent. Weird rule. When you have a ring with one substituent, you don't number it. As soon as it's 2, it doesn't matter where they at, you number them. All right. How'd that apply to this? We wanted to actually 4 carbons, no multiple bonds, 1 ring. You're going to see there's only 2 structures here. So 4 carbons with 1 ring. What are we going to call that thing?
Cyclobutane.
There's no other way to do 4 carbons and get a different structure. So the next one must be 3 carbons, and where are we going to put the 4th one?
Oh, okay. Thank you for doing this, because it actually kind of validates my I was doing the first problem on worksheet 20. You'd have a methyl on
Yep.
the end there.
So methyl cyclopropane. And can you make out a ring out of 2 carbons?
No.
Mm-mm. If I try to do that, I've actually just made a single carbon-carbon double bond. And it says no multiple bonds. So that's our only 2 answers. That's the only way to do 4 carbons. Alright, and we're not going to do these. We are going to do this guy. So what are my 2 substituents?
So one would be an ethyl and the other would be a methyl.
Mm-hmm.
Ethyl goes first because it's first in the alphabet. So you would have one ethyl, 2 methyl, pentane, yes, cyclopentane.
Very good. Don't need to do the other 2. We've actually already done them. I don't know why I still have them on this slide. I should update that with more rings. Actually, let's do another ring just because we got the space. I'm going to do slightly harder.
Ooh. Okay. So, let's see here. You would have, we'd start with 1 bromo, it's methyl, so 1 bromo, 3 chloro, 2 methyl, cyclopentane.
Very good.
Oh, Morgan, sorry. I should be letting you do some.
No, you're good.
Alright, cool.
That's a CL.
You want me to get this one, or?
The trick is the numbering. Which one is the number 1 location?
Again, it would be bromine.
It is not.
Oh, is it?
Bromine's at number 2.
Why are we saying ethyl
Shortest
is at
way to
number
number
1
it is
then, or-
still 1, 2, 3.
Uh-huh.
So your number 1 is either chlorine or methyl.
Oh, so, well, chlorine is the closer to A.
That's right.
I'm not sure how to say higher ranking in alphabetical order, but so it would be 2 bromo, 1 chloro, 3 methyl, cyclopentane. Okay.
Now, that right there is pretty much as complex as we get for a while. Having 3 groups off of a single ring. Most of the time we have 1 or 2 groups at most. Alright, next thing is our double bonds. Only thing we're going to do in a double bond is add the prefix E-N-E. Not prefix, the suffix E-N-E to say where that there's a double bond. And whenever you have an E-N-E, there's also a number The number tells you which carbon is the start of the double bond. So this is 2-butene and 2-butene, but there's also that's still a butene, but we're going to start at the 1. And there's only 2 cases where you don't have to number where your double bond is. Well, 3, kinda. So, do you think you need to number it there?
No.
Mm-mm. So ethene.
That would just be ethene.
And turns out you don't actually have to number it on this one either. Why does propene not need a number?
Oh, because if it was on the second one, it would just be rotated in space.
Right. That's exactly right. It's 1 propene no matter what. And then the last time you don't see it, gets back to our rings. If I have a single double bond in that there, what do you think we call that?
Cyclohexene.
That's right, without a number. The number is implied that one of those is the number 1 location.
Let's see here.
All right, now we're going to come back here to this geometry here in just a second, because you notice how we got this cis and trans? We're going to come back and talk about that in just a second. But let's actually back up to this and name these 5 in the middle now. So the 2 with the little red arrows were the easiest of these 2 to name. What do we think we're going to name these 2? We already kind of saw pentene. But where's the double bond start?
1 pentene.
Yep.
Guess we could say 1 pentene and then 2 pentene.
That is right. Don't worry about me. I just learning how to drink coffee apparently. Oh, that burns. All right, so right above that, what's our backbone on that one?
Let's see here. The backbone would be butene.
And right above it is still butene and butene yet again. Now, weird thing is, remember how we numbered it and we numbered it based on the substituents? You don't on alkenes. If you have an alkene, a double bond in it, you number it based on getting the alkene to have the lowest possible number. So, well, actually, let's start at the top. So, if I'm doing that on the top one, where is my number 1 carbon? On the right or the left? It's over here.
Number 1 carbon. Oh, it'd be on the right.
Because I want that to have lowest possible number.
That would be. So that would be 3 methyl, 1 butene.
That is correct.
Oh, okay. So then on the second one, it doesn't matter which one you start from, except that if you start from the left, you have a smaller number for the methyl. So you would have
that's like
yep. So you would have 2 methyl, 2 methyl, 2 butene.
That is right. Yeah, the substituent becomes a tiebreaker. And this one is probably easy
2
now.
methyl, 1 butene. I see.
Now, the only weird thing that pops up on these, and I'm going to do this on our introductory page here, where we first introduce these. So, right underneath where it says cis-2-butene, I'm going to write the other name that you might see for these. Cis still, and then but-2-ene. You will sometimes see the number that applies to the double bond before the E and E prefix.
Okay, little weird, but
Yeah.
all right.
They do that because we will see it's possible to have more than one functional group in the backbone. So if I have an ENE and this will end up with a YNE, that's not an L there, FYNE is for that triple bond. If I were to have a molecule with them both in there, so, and I'll do this over here too, so CH2, C, well that's a CH. I'm Russian. CH, single bond, C, triple bond, CH. It's a butene-ine. And typically, to actually distinguish what's going on, we number it as such. So this would actually be a but1-ene 3-ine. But that's where we get the numbers. Now, we're not going to see that at all. I'm just introducing that to explain why you sometimes see the numbers in the name like that. All right, but the prefixes here, cis and trans, they have to deal with how the backbone goes. So you see on this backbone, the two sides go up on the same direction. And yet here they're kind of staggered to one another. That is the difference between cis and trans. Cis is always going up with each other. Trans are always zigzagging. Now, we don't use that term on rings because rings are pretty much always going to be cis, but we don't actually say cis cyclohexane. And we would not have that with 1-butene because this side here, having two hydrogens, if I get rid of that and draw it out more like this, since it wouldn't matter how I switch those, there isn't a cis or trans 1-butene. There's just 1-butene. Okay, now after this we have some practice, but I'm definitely going to do a different number, different structures here. And then we're going to start talking about functional groups and naming some of them. But I'm actually going to stop right now because I think we've actually done enough damage to your psyches and your mind. But you should be able to actually get through the nomenclature for most all hydrocarbons. Now, going on the internet and getting help on this is going to be interesting to say the least. And it's mainly because if I do the real IUPAC nomenclature rules and bring up a good source like Wikipedia that does do a really good job of explaining them, you'll see that we're getting a very small section of the nomenclature because here's the actual rules. You know how complex it gets, up to 7 different steps rather than just 3. And the reason that's all in there is because if you want to name something with a lot more things than just carbons and hydrogens, which is what this thing is, there is a lot more rules that get applied. And we're not going to get anywhere this involved. This is an organic chemistry class, so if you are going to get there next spring or next fall or so, you are going to eventually get to this. And getting through these rules will be a piece of cake then, but you're going to be spending a lot more time on it. So it is there eventually for most of my students, but we don't need to worry about it yet. Now, what we will be doing next time is looking more at these functional groups and how we can identify them. And we will learn how to name some of them, but not anything past ethers on this page. So we won't do any naming of ethers, aldehydes, ketones, carboxylic acids, carboxylates, esters, or any carbonyl groups. So, but look how crazy this is. Don't you just really want to dig out the book and learn every single one of these? No.
Yes, certainly.
Do both of you get to take organic next year, or are you both done with chemistry now?
I think I'm done with chemistry.
I'm not sure, but hope not.
Are you not sure because you're not sure your major?
I don't remember what classes I have to take.
Oh.
Because, like, this is my last semester at CF.
Yeah, and then you're going on to the real university?
Yeah.
Which one you going to?
I applied to both UF and UCF, so if UF accepts me, then I'm going there.
You're closer?
Yeah.
What'd you do?
How old are you?
I'm 22.
Oh.
Oh, okay. I thought you were a lot younger than that.
Yeah.
Okay.
What about you, Kelly? What's next term for you?
Well, I'm taking the summer off to do stuff with my family before I go start taking college seriously, but I should only have next fall before I'm done with my AA.
Oh, and then you're off to
Pretty sure.
what are you thinking about majoring in?
Well, computer science is profitable, but I don't exactly want to do that for a living. But then again, journalists don't really make any money either, and it's easy to be a sad and soulless journalist, so I really don't know.
Yeah, those two would be a tough call right now, I think. I think journalists could be fun, but I'm right there with you. I don't have a lot of respect for most of the field right now.
Yeah. Which, I mean, hey, it'd be freaking awesome to go off to wild and interesting places and interview people during wartime and all sorts of stuff. But, I could easily be stuck doing the weather column in a Midwestern town's newspaper. I mean,
Yeah. Well, my wife has a friend from high school. He still does movie reviews. He used to love that, but now that journalism has changed so much, there's no real local movie reviewer. You have to be syndicated and whatnot. So he said the competition's just ridiculous now.
yeah.
And he doesn't want to sell a soul and do things. He says it's easy to get stuff published if you take a political stance on certain things in the right location.
Oh, definitely.
He said he was the one that said you gotta treat it like big time wrestling. There's no bad noise. There's no bad noise crowd other than silence. You want them to hate you or love you. And he says that's what the journalists do now. You got to get them to hate you or love you, but nothing between.
Yeah. I kind of started thinking about maybe doing journalism because of Stephen Fry and Christopher Hitchens, very interesting people. But I think one of them said that it was very easy to write columns and opinions that trashed things because articles like that just write themselves.
Yeah.
It's so easy to be pissed off about something that.
Well, and we have so much of that. That's probably why there's a lot of people that don't trust the media so much, because they do seem like they just want to wallow in the negatives.
And if you were to write something positive in favor of something, it just sounds kind of pithy and just it seems to lack substance, even if it doesn't.
Yeah, there's been a few times when journalists have been able to pull it off, but they're limited range. I mean, Good Morning America I used to view as that. It was always the fluff pieces. It was always the good news stuff. And there was definitely a good thing about watching it, because of that. But
yeah,
that mostly changed when I was in college, and it stopped being the total fluff piece. Because, I mean, you can't be doing that when people dying in place of the world. You can't just ignore the news when it's not positive. So
I mean, which, hey, disaster sells.
Yeah.
People love watching horror and destruction and death and misery on the TV. It sells.
To be honest, though, of those two, I think I'd rather be the weather reporter in Des Moines, Idaho, or wherever, rather than go into computer programming for a living.
Yeah.
System administration sounds like it could be fun, but I've done the programming, and the people who want your programs are just miserable SOBs.
Yeah. I mean, I don't really like programming all that much. I mean, it's a cool thing, but if I want to do something, I either just put something together that just barely gets it done, or find somebody else who's done it properly.
Yeah.
I don't really. It's not really my thing.
My friend is in computer science and she hates it, but she got a scholarship in high school and it pays for. I think it pays until masters or something. So she was like, "Well, I guess I'll do this," and she hates it. She really does.
It's the users that I think are the biggest problem. I mean, we talk about how negative social media can be, but it's all of the internet. You get the unfiltered venting on things, and I don't know. I when I contribute code anymore, I typically use burner email accounts and set them up and post my review with the fixes, and then cancel that account, so I don't have to deal with any of the feedback that comes along with it.
Oh shoot! Oh, that's funny. Well, I think I might have fixed it, but I don't want to hear it when something else screws up, and then they want me to fix it.
Oh, there's one that has my name on it that I still get emails on, and all that was there was so NetX for Microsoft. There is a compatible alternative for Linux, and for a while it stopped building properly, and it was because Bash changed how they were handling integers, and so the NetX thing, it had to calculate a magic number, and it was always coming up with one value short because it was calculating the integer wrong. Well, I submitted the code fix for the NetX alternative people and Bash on how to catch it, but then in my write-up I put in there that anybody who's trying to build it now, just build it under Xterm. Xterm doesn't have any of the bells and whistles, so just it'll work. And I didn't think much of it because I just moved on it, but I'll still get emails periodically. Have you looked into fixing this lately? It's been fixed for like 4 years. So I kind of just want to have an automatic reply that if you ask me if to fix it, I'm just going to tell you to update your system because it's been fixed. It was fixed shortly after I submitted the code changes.
Oh Jesus, that's funny. Just compile it in a different terminal.
Yeah, I did get a kick out of that because it's like once I figured out what was going on, I'm like, well, heck, no one's updated Xterm in like decades, so I wonder if this will work. And you don't even have to exit Bash to do that. You can actually type in Xterm, type your command, and it's fine. Because it just basically tells Bash to do this line under Xterm, and it worked fine. But
Jesus.
I did get a kick that, wait, we're messing up on integers in the 2000s on a computer. And I think I figured out the largest the integer could be, according to what NetX is using right now for its algorithm, it will never be anything larger than 32,000 without being totally rebuilt. And the largest magic number I've seen is like 512 or something like that. And almost all of them use the exact same magic number. So I do get a kick.
Yeah.
You don't even need to calculate it. We could just program. Use 512 all the time. It'll work.
What is NetX?
Thinking about it as a programming library. So you know how Windows programs, most of them have the same type of start menu and panel and file menu and whatnot. NetX helps
Yeah.
provide that to programmers, so you have that uniform look and get all the borders the right size, and gives you more direct access to certain components of the computer. I think that's a good enough
See.
example of that.
Yeah.
It makes it seem like it's a lazy way to do programming, but it's not really, because you have to know NetX to actually utilize it. It's just, for a Windows programmer, Windows developer, it's the best thing to get real access to the computer and make it do some fast things.
Yeah. I don't know. I've never really been able to figure out the logic behind